In this video, we will solve a worksheet about chemical equilibrium. It's for chemistry AP level. This worksheet, it's made up of three sets, set A, B, and C. I'm gonna leave you in the description box all the worksheets for sets A, B, C, but I will solve with you set A only, the rest B and C for your practice. Number one, let us start. Part A, what is the equilibrium constant expression for the reaction? The equilibrium constant, as you know, it's symbolized by K. We include only gases and aqueous because simply solids and liquids, they have constant concentration. And it's the concentration of the product raised to their stoichiometry over the concentration of reactant raised to their stoichiometry. So solid we don't include, we will include the gas. So it's the concentration of H2 to power of 4 over the multiplication of reactant concentration. This solid we will not consider. I consider only gas, so it will be H2O to power of 4. So this will be the answer. Part B, the equilibrium constant for the reaction. I have this reaction, 2NOCl gas to produce 2NO gas plus Cl2, and it's given to me K. What is the equilibrium constant Kc for this reaction? The relation between this reaction and this reaction is that this one, it's the opposite of this one and divided by 3. When I want to relate the opposite and divided by 3, first of all, I will assume this is K prime. Opposite, it means 1 over K, if this is K. And because divided by 3, so it will be cube root 3. So it will be 1 over K, 1 over 3 or cube root 3, which is 1 over radical, cube root radical of 2.4 times 10 negative 7, and K prime, the answer will be 1.6 times 10 to power of 2. As you see here, there are answers, but I'm solving for you in detail to get into the answer. Now, part C, given the following equilibrium equations and their corresponding equilibrium constant, find Kc for the following reaction. If I have to take a close look on this reaction, I see that it's just the summation of the above two. How? If I add these two equations, 2O2 and 2O2 subtracted, because as you know, if one in the product, other in the reactant, we do subtraction. If they are on the same side, we add. And we are left with CH4, I write it as it is, CH4 gas, 2CO2 minus CO2, because one in the product, one the reactant, and I put the answer in the larger side, so plus CO2 gas to give me H2O and 2H2O. I subtract and put the answer on the larger side, so H2 gas plus this one, nothing to add or subtract. So it's just the summation of the above. In the summation, we multiply, if the equations are summed up to a certain equation, we multiply the constant equilibrium constants in order to find this K. I'm gonna call it this K prime, which is 6.1 times 10 to power of 8 times 1.2 times 10 to power 14, and the answer is 7.3 times 10 to power 22. As you see here, this is the answer and this is the method. For number 2, a mixture of 9.22 moles of A, 10.11 moles of B, 27.83 moles of C, placed on a 1 liter container, so volume 1 liter at a certain temperature. The reaction is allowed to reach equilibrium, and at equilibrium, the number of moles of B 18.32. Calculate the equilibrium constant. So this mixture allowed to react, the reaction allowed to reach equilibrium, and he gave me the equilibrium number of moles of B. First of all, I will construct the equilibrium table, the ice table, which is the initial step, and then in molarity, and then change by reaction, and the last step, which is the equilibrium step. Since I will use the molarity, why? Because later I want to calculate the equilibrium constant, which includes concentrations. So let me find the initial concentrations for each one. So the initial concentration for A is the number of moles, which is 9.22 over 1, which is 9.22 molar. The initial concentration of B, 10.11 over 1, which is 10.11 molar. And the initial concentration of C, 27.83 over 1, which is 27.83 molar. And also given to me the equilibrium moles of B, I will change it to equilibrium concentration, which is number of mole over volume, which is 18.32 over 1, which is 18.32 molar. Let me construct now the table and substitute with the numbers. The initial 9.22, this is 10.11, and this is 27.83. At equilibrium, it means this step, the concentration of B, it was found 18.32. As we can see, initially 10.11, which means that something got added to 10.11 to reach 0.32. So the minus, the change by reaction, from C, it will be the minus side. It means from the right hand side will be the minus. I will take a quantity from the right hand side such that to add a quantity to the left hand side. As we know, the step change by reaction subjected to stoichiometry. The amount taken, I don't know, I will assume it X, but subjected to stoichiometry, so this will be 3X plus 2X and plus X. At equilibrium, it's the summation, as usual, of the above two steps. 920.22 plus X, this is given to me, and this is 27.83 minus 3X. Now I want to solve for X, because once I know X, I will be able to find K. So we will continue solving for X. We can say, but 10.11 plus 2X equal 18.32. So we will solve for X, but 10.11 plus 2X equal 8.32. In simple calculation, X equal 4.05. Now let me write the equilibrium constant. K equal, according to this reaction, it's C to power of 3 over A into B square. Okay, the concentration of C, it's 27.83 minus 3 times X, which is 15 point. Okay, let me write for you first of all in details. So the concentration is 27.83 minus 3 times X. X, I found it 4.105, and all of it to power of 3 over the concentration of A, which is 9.22 plus 4.105 times the concentration of B, which is 18.32 to power of 2. And the final answer will be, definitely I do the simple calculation, and the final answer will be 0.832. So this is the answer, and this is the method. Now we will move to number 3. At a certain temperature, it's given for me the K equilibrium. Assume that the equilibrium is established at the above temperature by adding only IBR to the reaction flask. What are the concentrations of I2, BR2 in equilibrium with 0.0124 moles per liter of IBR? Okay, let me write the equation and construct the ice table in order to find the concentrations of I2, BR2 at equilibrium. So in equilibrium with I2 gas plus PR2 gas, and I will construct the table which is ICE, and this is in molarity. He didn't give me any initial concentration because this one given to me for IBR, it's the equilibrium one. So I'm gonna assume it X, nothing added at the beginning, since he said assume the equilibrium is established at the above by adding only IBR. So at the beginning, no I2 and BR2. By time, X will be dissociated into, I don't know what amount, I will call it Y amount. And don't forget the dissociation and the addition subjected to stoichiometry. So here 2, so minus 2y, this is 1, so this will be y, and this is 1, this will be y. Equilibrium, it's the summation of the above two steps. So x minus 2y, and this is y, and this is y. I can get the benefit to construct equations. I have that IBR at equilibrium is 0.0124. So the first equation I can construct is that x minus 2y equals 0.0124. This is the first equation that I can construct. Now let me find K. K equal the concentration of I2 times BR2, all divided by IBR. Let me substitute. K is given to me its value 4.13 times 10 negative 2 equal y times y at equilibrium, which is y square over x minus 2y. And x minus 2y, I have its value, which is 0.0124. So 4.13 times 10 negative 2 equal y square over 0.0124. I can cross multiply to find y square and then radical the answer. So y square equals 6.35 times 10 negative 6, and then radical the answer to find y. So y equal 2.52 times 10 negative 3. But y is the concentration at equilibrium for I2 and BR2, which are the two concentrations that he is asking about. What was the initial concentration of IBR? It means we want to find x. Okay, we have this equation, we will use it, x minus 2y. Now we have y, x minus 2y equals 0.0124. So x minus 2, value of y, we found it in part A, 2.52 times 10 negative 3 equals 0.0124. So solving for x, it will be 0.0174 molar. In number 4, 0.24 mole of A is placed in 1 liter container at 700 degrees, where it is 38.8% dissociated when equilibrium was established. What is the value of the equilibrium? Okay, again, I'm dealing with equilibrium. So I will construct the table. At the beginning, we have 0.924 in 1 liter, which is the concentration and overview, which is the same. So I stable. So 0.924 at the beginning, no concentrations for B and C. By time, definitely we cannot take any concentrations from 0, so minus will be from the left side. Change by reaction always subjected to stoichiometry, so minus 3x, this is 5x and 2x. The equilibrium is the summation of the above two steps, so 0.924 minus 3x, this is 5x, and this is 2x. This is the equilibrium stage. I can benefit from the given to find x. He said that 38.8% dissociated. We know that the percentage of dissociation equal to the amount dissociated over the original amount multiplied by 100. Okay, the amount dissociated 38.8, so 38.8. I will take this 100 to the other side, so over 100. Amount dissociated is 3x. This is the amount dissociated over the original amount, which is 0.924. Cross multiply to solve for x, so x equals 0.119. Now we found the value of x, so it's easy to find k. From the equation, k equal B, concentration of B to power of 5 times C to power of 2 over A to power of 3. Just now I will substitute. B is 5 times x. We found already x, which is 5 times 0.119 all to power of 5. C, which is 2x, so 2 times 0.119 all to power of 2 over A. A, it's 0.924 minus 3 times 0.119 and all to power of 3. And the final answer will be 0.0231. This is the value of K. For number 5, the equilibrium constant for the reaction is 2.6 times 10 negative 3. If 0.80 mole of NO and 0.223 mole of each of N2 and O2 are mixed, this is the initial quantity in a volume 1 liter. What are the concentrations at equilibrium? Okay, first of all, I will find the initial concentration for each one from the given. It's the number of mole over volume, which is 0.820 over 1, which is 0.820 molar. And the initial concentration for N2 equal to that of O2 equal to 0.223 over 1, which is 0.223 molar. Okay, and let me construct the ice table to find the concentrations at equilibrium. So 2NO gas to give me N2 gas plus O2 gas. Okay, now ice table, I, C, E. Okay, the initial for NO, it's 0.820, I found it, and this is 0.223, 0.223. Here I don't know from where the dissociation it will start, so I have to find the reaction quotient, because the Q, which is the reaction quotient, will lead me, I will compare it to the value of K to see how the reaction proceeds. So this we call it reaction quotient, which is the quotient of the equilibrium at any instant, not at equilibrium position. Okay, which is the multiplication of concentration of products raised to their stoichiometry over the multiplication of reactant raised to their stoichiometry. Okay, the concentration of N2 and O2, 0.223 each, so 0.223 to power of 2 over NO square, and NO is 0.820 square. So now just I do the calculations, so Q will be 0.0739. Let us compare it to K, but K, it's given to us 2.6 times 10 negative 3. But K is 2.6 times 10 negative 3, which is smaller than Q. So Q is larger. Q is greater than K. So that backward reaction is favored such that to lower it. Why? Because Q is equal to the concentrations of product over reactant. So to reach equilibrium, Q should be lowered. Right? If Q should be lowered, it means that this is to reach equilibrium. To reach equilibrium. Why? Because Q is greater than K. To reach equilibrium, it should be lowered to reach the value of K. So if Q is lowered, it means the product should be lowered and the reactant should be high. So minus will be from the product side, and as we always say, subjected to stoichiometry. So minus from the product, so plus from the reactant. So 0.820 plus 2x, 0.223 minus x, 0.223 minus x. Now K equal, now we can solve for x. K equal as the product here over this square. So 0.223 minus x to power of 2 over 0.820 plus 2x to power of 2, which is equal to the k given in the given, 2.6 times 10 negative 3. Now to solve for x, I radical both answers, and 0.223 minus x over 0.820 plus 2x equal, because the radical is to the 2, it's square radical, so we have to write in reality plus or minus 0.051, but this minus, it will be neglected because the answers will not follow. You can check it, will not follow the values, the correct values. So here, solving for x, it will be 0.164. Once I solve for x, I can find the equilibrium concentrations as it's required. So NO equilibrium is equal 0.820 plus 2 times 0.164, which is equal 1.15 molar, and the concentration of N2 at equilibrium equal the concentration of O2 at equilibrium, which is equal to 0.223 minus x, which is 0.223 minus x, which is 0.164, and the answer is 0.059. And like this, we solved this problem. So 1.15, this is for NO, this is 5.59. Okay, let me, okay, 5.9, okay, 0.059 molar.